Hello. We'll start the problem solving session. Hello. Am I audible? Hello. All right. Welcome to week 6 of problem solving sessions for the digital electronics course on nptel 2024. I am your instructor Sachin Sampath from the Indian Institute of Science, and we'll get right into the problem solving. Okay, the first question is, in the figure given below, the outputs of F1, F2 and F3 respectively when x equals 0 and y equals 1 is, and the circuit is as follows. As you have learned in class, this is the circuit of a single bit magnitude comparator, except that the y and x are switched here. So f1 is the function y is greater than x, that is if y is 1 and x is 0, f1 should be high. f2 is the function x is greater than y, so if x is 1 and y is 0, then f2 should be high and the other two should be 0. f3 is the function x is equal to y, so if both x and y are 0 or both are 1, then f3 will be high. And that does happen. And how does it happen? This here is a xy complement. This output is y times xy complement, the whole complement, and it is passed through a NOT gate, which is an AND gate with both inputs tied to the same input, so it's a NOT gate. So this is y times xy complement, which is y times x complement plus y complement, which is yx complement, which is true, or which is 1 if y equals 1 and x equals 0. So that shows that y is greater than x. Similarly, this output is x times xy complement, the whole complement, and f2 is x times xy complement, which is x times x complement plus y complement, which is xy complement, which is 1 if x is 1, y is 0, so if x is greater than y. And here similarly this output will be y times xy complement, the whole complement, into x times xy complement, the whole complement, which will be nothing but, if you simplify it, you will get xy bar, we get xy plus x bar y bar, which is equal to 1 if x equal to y equal to 1 or x equal to y equal to 0. So in this case, since y equals 1 and x equals 0, y is greater than x, so f1 is 1, f2 is 0 F3 is also 0. We'll go to question 2. I'll explain question 1 again. So in the figure given below, the outputs of F1, F2 and F3 respectively when x is equal to 0 and y is equal to 1 are. That is the question, and the circuit is given there. So from the lecture, you can see the working of the circuit. The circuit is a magnitude comparator circuit for a single bit inputs. So the first function, well, I'll explain everything again since two more people joined. So this is the question. The figure given below, the outputs of F1, F2 and F3 respectively when x is equal to 0 and y is equal to 1 is, and this is nothing but a single bit magnitude comparator. So if y is greater than x, with a single bit, the only possibility is y is 1 and x is 0. Then f1 will be 1. If y is less than x, that is if y is 0 and x is 1, then f2 will be 1. So this is the function. This is y greater than x, this is y less than x. And if y is equal to x, the function f3 will be equal to 1. So this is the function y is equal to x. And I'll explain how the circuit will do that. So firstly, this output is xy complement. This output is y times xy complement, the whole complement. So that will be passing through this NAND gate, and both the inputs of the NAND gate are connected to the same input. So this is A and this is also A. Output will be A times A whole complement, which is nothing but A complement. So that's a NOT gate made using a NAND gate. So F1 is nothing but y times xy complement, which is nothing but y into x bar plus y bar using the De Morgan's laws, which is nothing but yx bar plus y bar, and y bar is 0, so it is nothing but yx bar. So we can write this as yx bar, and you can see that this yx bar will be equal to 1 only if y is 1 and x is 0. So if y is 1 and x is 0, that means y is greater than x. So that is f1. Similarly, here you will get x times xy complement, the whole complement. So f2 will be the function x times xy complement. Hello. Sorry, it seems I was muted for the entire time. I'll explain everything again. So you have seen the question and the figure. They're asking if x is 0 and y is 1, what is the output. And what I explained just now is the function f1 is nothing but yx bar. So yx bar is 1 when y is 1 and x is 0. So which is what is given as input here. So since y is 1 and x is 0, f1 will be equal to 1. So y is 1, x is 0 means that y is greater than x if it's just a single bit, because 1 is greater than 0. Similarly, here in the bottom portion, f2 will be equal to x times xy bar, which is nothing but x times x bar plus y bar, which will be nothing but xy bar. So f2 is xy bar, which is 1 only if y is 0 and x is 1. So that means x is greater than y for a single bit. So it's comparing whether x is greater than y or not. If x is greater than y, f2 will be equal to 1, otherwise it will be 0. So in this case, y is 1, x is 0, so f2 will be 0. Now the final thing remaining is f3, and f3 is, so let's call this c and let's call this d. So what's coming here is c, here is d, it's cd complement. This is a NOT gate, so it's called cd complement whole complement. So f3 is cd, which is y into xy complement whole complement times x into xy complement whole complement, which is y bar plus xy into x bar plus xy, which is y bar x bar plus y bar xy will be nothing but 0, plus xy into x bar will be 0, xy into xy will be xy. So it's xy plus x bar y bar. This is equal to 1 if both x and y are 1. So in that case, this will go to 1, this term will become 1, this term will become 0. Or another possibility is if x and y both are 0, that case this term will become 1 and this term will become 0. So it's checking if both x and y are the same bit value or not. So it's checking if they are both equal. And in this case, y is equal to 1 and x is equal to 0. So both of them are not equal. So f3 will be equal to 0. And this particular circuit is called a magnitude comparator. And this is a 1-bit magnitude comparator because each input is of 1 bit. So the function f1 was yx bar, which is the same as a function y is greater than x. Function f2 is xy bar, which tells you whether x is greater than y. And function f3 is xy plus x bar y bar, which is the same as checking whether x is equal to y or not. Okay, that was the first question. Next we will go to question number 2. Suppose we want to compare two 8-bit binary numbers, and the numbers are given denoted as x, which has 8 bits, x7, x6, x5, x4, x3, x2, x1, x0, and the second number is the number y with its 8 bits denoted as y7, y6, y5, etc., y2, y1, y0. What will be the correct Boolean expression that can detect if x is greater than y. And they have given that gi is the expression xi yi bar or xi yi complement, ei is xi yi plus xi complement yi complement, and li is xi complement yi. So that is the question. And the solution is as follows. First, we have to note that gi is the function xi yi complement, which is same as f2 in the previous question, which checks if x is greater than y. Ei is the function xi yi plus xi bar yi bar, which is the same as function f3 in the previous question, which checks if x and y are the same bits. Li is xi bar yi, which checks if it's the same as function f1 in the previous question, which checks if yi is greater than xi or if xi is less than yi. And the index I denotes which of the bits we are checking. There are 8 bits in each number, so I can go from 0 to 7. So first, just we'll take an example to see when you can say a number is greater than another number. If it's 1 bit, then 1 is greater than 0, 0 is less than 1. They means the same thing. So if you write the truth table, or x greater than y is what they're asking, right? For a single bit, write the values of x, y. Say x is greater than y. When is it true? When both are 0, x is the same as y, so this is not true. So this will be 0. When x is 0, y is 1, x is less than y, so this will be 0. When x is 1 and y is 1, both are equal, so this will be 0. Only when x is 1 and y is 0, x is greater than y, so it will be 1. That is only for 1 bit. Suppose x and y had 2 bits, 2 bits each. Let's take some number. Let's say 1 0 and 0 1. When we are comparing, we start at the leftmost position, the MSB. We check if the MSB is greater. MSB of the first number is greater than the MSB of the second number. 1 is greater than 0 from this truth table. So we automatically say that the number 10 is greater than 01. Suppose the numbers were in opposite order. We are checking if 01 is greater than 10. Then you would check the MSB. They're not the same. So you check if 0 is greater than 1 or if it is lesser than 1. 0 is actually lesser than 1. So you would say 01 is smaller than 10. Similarly, suppose you had a 3-bit number 110 and 101. Let's say this number is 6, this is 5. 6 is greater than 5, right? How would you check in binary? You check the MSB. MSB is equal for both numbers. So if MSB is equal, you move to the bit that is to the right of the MSB. So we move to this bit. We check if the bit in the first number is greater than the corresponding bit in the second number. Since 1 is greater than 0, we say that the entire number 110 is greater than 101. So if you had to check numbers 111 and 110, Then we check the MSP, both are equal. We check the bit next to the MSP to the right of the MSP, those are also equal. Then we move one position to the right again. We check these two numbers and we see that 1 is greater than 0. So we can conclude that 111 is greater than 110. So that is how magnitude comparison happens. So what it means if you have 8 bits is, first you check the bits x7 and y7. If x7 is greater than y7, then uh, the number x is greater than y. So your output function f, which says if x is greater than y, will be, first it will check the bit number 7. If x7 is greater than y7, then it's greater, so that is nothing but g7. So if g7 occurs, that means g7 is x7 y7 bar. So if g7 is equal to 1, then that means that x7 is 1 and y7 is 0. In that case, x will be greater than y. Or another possibility is, if x7 is equal to y7, that is if e7 is true. Another possibility is e7 is true, but x6 is greater than y6. We move to one bit to the right. So we checked the bits x7 and y7. We move one bit to the right. That is x6 and y6. Now if x6 is greater than y6, g6 is true. Then also the number x is greater than y. Similarly, if both 7th and 6th bits are equal, but the 5th bit of x is greater than the 5th bit of y, that is g5 is true, then it's again x is greater than y. So you keep on, this will go on the same pattern, e7, e6, e5, g4 plus e7, e6, e5, e4, g3 plus e7, e6. I'll skip a few terms and the last term will be e7, e6, e5, e4, e3, e2, e1, g0. That is, the two numbers are equal in all other places except the 0th bit or the least significant bit. So that is the Boolean expression to detect if the number x is greater than y. We'll go to question number 3. Which of the following statements is or are false? That means multiple statements can be false. First statement, gray code is a sequential code. So this statement is false. A sequential code, so in a sequential code, the code word coming after some given code word can be obtained by adding 0001, adding 1 to it. For example, if you have a XS3 code In an XS3 code, the number 0 is represented by 0011, the number 1 is represented by 0100, 2 is represented by 0101. You can see to 0011, if you add a 1, it will become 1 plus 1 0 with 1 carry, 1 plus 1 0 with 1 carry, 10100. That is the next number. You get that by adding a 1. Similarly, in an this is XS3. Similarly, in 8421 code, number 0 is 0001. The number is wait. Number 0 is 0000. Number 1 is 0001. Number 2 is 0010. So by adding 1 to 0001, get 1 plus 1 is 0 with 1 carry, you'll get the next numbers. So that type of code is a sequential code. And if you observe in gray code, 0 is 0000, 1 is 0001, 2 is actually 0011, and 3 is 0010. So if you add a 1, 0001 plus 0001 should get 0010, but you get 0011. So it's not a sequential code. But each of the numbers in a gray code differ by differ in only one position, so they become part of a cyclic code. Okay, that's the first statement. Second statement, in ASCII code, capital A is 1000001 and small a is 1100001. This is a true statement. Capital A is 65, which is 64 plus 1. So if you write it in binary, these are the weights. So it's 1000001, which is the same as this thing. And small a is 97, which is 64 plus 32. That's 96 plus 1. So if you write it in binary, 11000001. So that's the number given here. Okay, so that statement is true. Third statement, for XS3, so denoted as XS3, the allowed values are from 0011 to 1100. So this is also a true statement, because in XS3 code, the code words are, you have decimal 0, 1, 2 up to 9. So in binary, the representation will be 00000001 up to 1001. You get XS3 by adding 3, that is 00112, to the binary code. So you'll get from 0011 0100 up to 9 plus 3 is 12, which will be 1100. So this statement is also true. Finally, the fourth statement, binary to gray as well as gray to binary code conversion use only XNOR gates. This statement is false because while converting from binary to gray, for example, if you have the number 1000, if you want to convert it to gray, you take the MSB as it is, then you XOR the MSB and the bit next to it, it's 1, then you XOR these two bits, it's 0, then you XOR these two bits, it's 0. So you're doing XOR operation, and they've said that it uses only XNOR gates, so it is false. Then we go to question number 4. In an ALU block, the engineer had selected the following logic: if S is equal to 0, Y0 is AB complement, we'll write it this way, Y1 is A plus B complement, else if S is equal to 1, Y0 is A complement B plus AB complement, and Y1 is AB. Write the simplified expression for Y0 and Y1. So there's a block like this and two inputs A and B and two outputs Y0 and Y1, one select input, and depending on what the select input is, he wants different operations to be performed. Okay, so here we can see that when S is equal to 0, Y0 is AB complement, S is equal to 1, Y0 is A complement B plus AB complement. So you can write Y0 as S complement into AB complement plus S into A complement B plus AB complement. So what happens when S is equal to 0? This term will become 0 and this will become 1. So we'll get AB complement. When S is equal to 1, S bar will become 0. So this term will go to 0. S will be 1. So I will be left with A complement B plus AB complement. But they have asked us to simplify this. So the simplification, you will get S complement into A complement plus B complement plus SA complement B plus SAB complement, which is S complement A complement plus S complement B complement plus SA complement B plus SAB complement. This can be further written as, you group these two terms, you will get A complement into S complement plus SB, plus you group these two terms, B complement into S complement plus SA, and you use the distributive law of addition over multiplication. That is, this can be written as S complement plus S into S complement plus B, and this can be written as S complement plus S into S complement plus A. So this will be A complement to S complement plus B plus b complement into s complement plus a. So you expand that and write it. You will get s complement a complement plus s complement b complement plus a complement b plus ab complement. That is for y0. For y1, again similarly, when s is equal to 0, y1 is a complement b plus ab complement. S is equal to 1, y1 is ab. So you can write y1 as s complement into a complement b plus ab complement plus sab, which is nothing but s complement oh sorry, there was a mistake. When s is 0, y1 is a plus b complement. So this is a plus b complement. So that will be s complement into, use De Morgan's law, s complement into a complement b complement plus s into ab. So that is the expression for y1. Okay, that's question 4. We'll go to question 5. Question 5 says the gray code of 125 base 8 is x if we feed x to a binary to octal converter, then the output octal number is. So first thing we have to do is find the gray code of 125 base 8. And to do that, the procedure is, first you write 125 base 8 in binary. So each of the digits you represent it in 3 bits of binary, that is 001, 010, 101. That's the binary equivalent. Then you convert it into gray code. So previously I explained the in this question how to convert to gray. So the MSB, you write it as it is. So it's 0. Then you XOR these two, that's 0. XOR these two, 0 XOR 1 is 1. XOR these two, 1 XOR 0 is 1. Similarly, keep XORing, you keep getting 1. So this is the gray code of 125 base 8. Now if you feed this into a binary to octal converter, then what will it do? It will group the bits from right to left, these three and these three, and then it will represent that in octal. So each group of 3 will be represented by one octal number. 001 is 1, 111 is 7, 111 is again 7. So it's 177 in base 8. That is what you will get as your result. Alright. We'll go to question 8. Question 6, sorry. the message 10111011 encoded to Hamming code protocol is. So what is the Hamming code for this message code word? So first we observe that 8 message bits. So we need to use a 12,8 Hamming code. So 12 minus 4, 8 is equal to 4 parity bits will be there. And the number can be represented in Hamming code as P1, P2, D3, P4, D5, D6, D7, P8, D9, D10, D11, D12, where the given number is 1, 0, 1, 1, 1, 0, 1, 1. Now to find parity bits, to find P1, we do D3 XOR D5 XOR D7 XOR D9 XOR D11, which is nothing but 1 XOR 0 XOR 1 XOR 1 XOR 1. When doing XOR operations of multiple bits, if there are an even number of bits, the output is 0. There are odd number of bits, the output is 1. So here there are 4 ones, which are, if there are even number of ones, then the output is 0. If there are odd number of ones, the output is 1. Here there are 4 ones, which is an even number, so P1 is 0. Similarly, P2, you find that by XORing D3, D6, D7, D10, D11. So what bits you should XOR, that you can decide in this way. So for P1 you XOR all those bits where this index has a 1 in the ones position. That means 3 can be represented as 0011. So this is the ones position. So there's a 1 here. In 5 there's a 1. In 7 there's a 1. In 9 and 11 there's a 1 in the ones position in all these numbers. So only those digits will be XORed for P1. For P2 you will XOR all those digits which have a 1 in the 2's position. So if you have 4 bits, 2's position is the bit next to the LSB. Then this will be the 4's position, this will be the 8's position. So you can see that D3, 3 has a 1 in the 2's position. 6 also has a 1 in the 2's position. 7, 10 and 11. All of these have a 1 in the 2's position. You will only XOR those bits. Similarly for P4 you XOR only those bits which have a 1 in the 4's position, and for P8 you XOR only those bits which have a 1 in the 8's position. Okay, let's find out P2. D3 is 1 XOR D6 is 1 XOR D7 is 1 XOR D10 is 0 D11 is 1 There are 4 ones again, so it's an even number of ones, so the XOR of all those will be 0. P3 is all those numbers, all those digits where the index is a 1 in the fourth position. So that will be D5 0101. Here there's a 1. XOR D6, 6 is 0110. There's a 1 here, the fourth position. D7 0111 has a 1 in the fourth position, and D12 1100, it has a 1 there, and that will be equal to D5 is 0 XOR D6 is 1, D7 is 1, D12 is 1. So there are 3 ones, which is an odd number of ones, so the output is 1. Finally, we generate the fourth parity bit, which has all those terms in which the index has a 1 in the 8th position, and that will be the number 8, 9, 10, 11, and 12. So these all have 1 in this last position. So you get D9. Actually, there's no D8 here because the 8th bit is the parity bit. So there won't be any D8. It starts from D9, D10, D11, D12. That's the XOR of the last 4 bits, which is 1 XOR 0 XOR 1 XOR 1. So you get a 1. So the bits are 0 0 and 1 1. These are the parity bits. Then you write the entire number in the given order. So that will be P1, P2, D3, P4, D5, D6, D7, P8, and then D9, D11, D10, D11, D12. This is the required Hamming code word. Okay, I'll be right back. Alright, I'm back. We finished question 6. We'll move to question 7. Question 7 is, in the below circuit, x3, x2, x1, x0 is equal to 1001, and y3, y2, y1, y0 is 1101. What will the value of, what is the value of m7, m6, m5, m4, m3, m2, m1, m0? So the circuit, give me a minute, I'll get the circuit. It's a big circuit, so I can't draw it. I'll get a picture of it. Just give me a minute. Okay, that's the circuit. I hope that's alright, it's visible. So in this circuit, what is the output value? M7, M6, M5, M4, M3, M2, M1, M0. And you can go back to lecture and see that this circuit is the same as a multiplier circuit, to multiply two 4-digit numbers, and the result will be the product of 1001 with 1101. So 1101 into 1001, which is the same way you multiply numbers in decimal. You can do it here. 1 times this, 1 times 1101 is 1101. Then you leave a blank space. Then you do 0 times 1101, which will give you 0000. Then shift by 2 places, multiply 0 times this 1101. That will again be 0000. Shift by 3 places and multiply 1 times 1101, which will be nothing but 1101. And then you add it. 1, 0, 1, 1 plus 1 is 0 with 1 carried over, 1, 1, 1. So that's the product, and that will be the output of this particular circuit. So M7, M6, M5, M4, M3, M2, M1, M0 is nothing but 1, 1, 1, 0, 1. 1, 1, 0, 1, 0, 1, and last bit will be 0. Okay, that's question number 7. We'll go to question 8. Just 3 more questions, 8, 9, and 10 left. Question 8. A receiver receives one message encoded to Hamming code 12,8 as 0011 0111101. It is suspected that D3, D5, and D6 could be corrupted. What will be the parity check outputs C1, C2, C4, C8 at the receiver end? So this is another question on Hamming codes, and so in lecture we saw that if D3, D5, and D6 are the corrupted bits, you should get C1, C2, C4, C8 is equal to 0000. If those three are the only bits which are erroneous. So once we calculate C1, C2, C4, C8, if it is 0000, then we could say that then there might not be any errors, or if there were three errors, then they should have been D3, D5, and D6. Or if D3, D5, and D6 were the only erroneous bits, you would get 0000 as your parity. So we'll check if what our suspicion is correct or is it wrong. For that we have to first find the parity bits, and the parity bits are nothing but the first parity bit is you take first check bit C1, you get it by XORing the first parity bit P1 with D3, D5, D7, D9, and D11. And as we saw in the other question, P1 was nothing but, to generate P1 we use D3, D5, D7, D9, and D11. So while checking, we'll XOR with the same exact bits along with P1 also. So while generating P1 we use this, and while checking we take those bits and XOR it with P1 also. Now let's see the number is P1, P2, D3, P4, D5, D6, D7, P8, D9, D10, D11, D12. That is 0011, 011, 11101. So P1 0 XOR D3 is 1, XOR D5 is 0, D7 is 1, D9 is 1, D11 is 0. So there are three ones here which are being XORed together, so we'll get output as 1. C2, similarly P2 with the same set of bits used for generation. to generate P2. That is D3 XOR D6 XOR D7 XOR D10 XOR D11. So if we do that, it's 0 XOR D3 is 1, D6 is 1, D7 is 1, D10 is 1, D11 is 0. There are 4 ones, so it's 0. C3 is similarly P3 XOR the same bits you used to generate P3. Oh, there's no P3, there's a C4 and a P4 because the index for the check and parity bits are powers of 2. So that's P4. To generate P4 you had used D5 XOR D6 XOR D7 XOR D12. Here for this question P4 is 1, XOR D5 is 0, XOR D6 is 1, XOR with D7 is 1, D12 is 1. Four ones, that is an even number of ones. So this is equal to 0. Final check bit is P8 XOR the last 4 digits, which is XOR of these 1 1 1 0 1. So 1 1 1 0 1, which is 0, since there are 4 ones, which is an even number. So finally the check bits are C1 C2 C4 C8 is 1 0 0 0. So the error that we suspected has not occurred. We had suspected D3 D5 D6 to be the errors, but if that was the case then C1 C2 C4 C8 would have been 0 0 0 0. Since it's not 0 0 0 0 and error not in C3 C5 C6. I mean it might be in one of these, it might be C3 C5, but it's not, and it might be in all of this along with something else like um I mean D3 D5 D6, D3 D5 D6 and D8 also might be erroneous. Something like that might happen, but only these three can be the errors. That's question number 8. So we saw both generation of Hamming code and checking errors using the Hamming code. We saw one problem in each topic. Okay, we'll move on to question 9. In the circuit diagram given below, if B is 1 0 0 0 and Y is 0 1 1 1, find A, and they have given that A, B and Y are in XS3 code representation. And give me a minute, I will get the circuit. So this is the circuit, and you can see that this, if you have seen the lecture video, this circuit does subtraction in excess 3. So the result y is a minus b in excess 3. So here what they have given, y is equal to 0 1 1 1, which is 0 1 0 0 in binary. So which is nothing but 4 in decimal. So this is actually 0 1 1 is 7. So in excess 3 we add 3 to the number. So 4 will be represented by the symbol for binary equivalent of 7. And they've also given b is 1 0 0 0, which is 8, but it's excess 3, so it's actually 5 in decimal. So they're saying y is 4 is a minus 5, so a will be 9 in decimal. Or excess 3, even you could get a negative number also. So 1 minus 5 is minus 4. So if y is if y is 4, it could have been, a could have been 1 also. And 1 in excess 3 is 0 1 0 0, right? And the way you tell the difference is by checking the carry out here that you get. So if the carry out is not there, then it is a let me check it. So there are two situations. If carry out is there, then that means your number a was bigger than your number b. So if C out is equal to 1, then your number a greater than b, so a equals 9, which would be 1 1 0 0 in excess 3. If C out was not there, that is, there was no carry out, C out was 0, then it means a was a number smaller than b. So your result is actually a negative number. So your result was actually minus 4. Then a is equal to 1, which is 0 1 0 0 in excess 3. So these two things are possible, but most of the time if you write only this positive number, that should be enough. Because they have not given you the carry out, you can simply assume that you got a carry out as 1. Depends on the examiner how they will check. Okay, question 10, last question for today. Suppose two 128 bits binary codes capital X and capital Y are to be compared by cascading series of IC 7485. How many such ICs will be required. So the IC7485 is like this. 7485, you have three inputs here. This is X greater than Y input, X is equal to Y input, and X less than Y input from previous stage if you are doing cascading. And you can give your data here: x3, x2, x1, x0, y3, y2, y1, y0, and you will get three outputs: whether your x is greater than y, x is equal to y, x is less than y. This is for the current stage. That is IC7485. Pin numbers you can find by looking at the datasheet. So what it means is, essentially, first if it will check whether x3, x2, x1, x0 is greater than y3, y2, y1, y0. If it is greater, it will give you high, this will be low, this will be low. That's what it will give as output. If suppose x3, x2, x1, x0 that is smaller than y3, y2, y1, y0, then that means regardless of the previous stage, it will give you x is less than y. So this will be high and the other two will be low. Next thing is, suppose x3, x2, x1, x0 is equal to y3, y2, y1, y0. Then what it will do, it will check the previous stage inputs. In that case, if x is greater than y in the input, if this input is high and these two are low, then you will get high, low, low. The overall number is high, is greater, is what it means. Suppose you get x is equal to y in the previous stage also, and x is equal to y in this stage also. That means the entire number, including the previous and current stage, both numbers are equal. So if you have low, high, low, they will get low, high, low. And one more specialty about this particular IC is, if this x is equal to y in the previous stage is high, and regardless of what is given to x greater than y or x less than y, then you will get low, high, low, as long as x3, x2, x1, x0 is equal to y3, y2, y1, y0. That's some extra built-in feature. And suppose x is equal to y in this current stage, but x was less than y in the previous stage. So this is high, this is low, and this is low. Then the entire number is lesser. So we'll get high, low, low, and high. So you can kind of understand why this is the case by checking with some number. If you have only, let's say, a 2-bit comparator, suppose you had a comparator which should compare x1, x0 and y1, y0. So it could compare only 2 bits. You could use two separate stages, x3, x2, y3, y2. You could give to one comparator, and then x1 x0 y1 y0 you could give to the other comparator. Simply set this all as low, the previous stage for the first. Then you take the outputs given here and give them as inputs in the next stage. So then now what it will do, it will check whether the two bits from left to right from the MSB are equal. If they are not equal, for example, if you have 1101 and 1110, then it will check these two bits, this comparator. Since both are equal, then it will use these inputs that you have, and those inputs are nothing but the output of the first comparator. The first comparator checks these two. It sees that 01 is less than 10, so it will give 01 less than 10. So it will give x less than y as high, and it will check. So in this way you can cascade uh, two input comparators to get a four input comparator. Okay. Now the question is, if you have 4-digit comparator that can compare two 4-digit numbers, then to compare 128-digit number, how many stages will there be in the cascade? You see that each of these comparators can take 4 inputs and compare. So if you have 128 bits, total by the 4 bits in one comparator, 4 bits per comparator. So you'll need 32 comparators. This is in cascade connection. Parallel, other types of connections are also possible that are explained in the lecture videos, so you can check that out. By not doing cascade connection, if you do parallel connection, then you can use lesser number of comparators to compare the same number of digits. Okay, that is it for today's session. If you have any doubts, you can ask me for the next 10 minutes. I will stay here, otherwise you can leave. I'll just go through briefly the concepts that we covered today. First question was on magnitude comparator for 1-bit numbers. Second question was on magnitude comparator for two 8-bit numbers. Third question, we saw gray codes, then ASCII code, XS3 code, and binary to gray code conversion. In fourth question, we saw just a simple logic design. In the fifth question, we saw how to get gray code of octal numbers. You first convert it into binary and then convert that binary number to the octal to the gray code of the corresponding binary number. Sixth question, we saw how to generate the parity bits for a Hamming code. Seventh question, We saw how to do multiplication in binary, multiple bit multiplication. Specifically, we saw 4-bit binary multiplication. Eighth question, we saw how to check when you check for errors when you receive a Hamming code word. Ninth question, we saw subtraction in excess 3 numbers. 10th question, we saw magnitude comparators using cascade of smaller magnitude comparators. Okay, that is it for today's session. Thank you for attending. If any of the people watching the recorded lectures have any doubts, you can mail it to me, or you can ask in the discussion forum, or you can attend the next session and get your doubts cleared. Thank you.